just like mentally done. All right. Here we go. More practice with growth and decay. We have studied half-life, which right now is the only form of decay that we've really worked with. But I want to show you some more problems. Decay occurs when your base number is less than 1. And the difference between growth and decay in the compounding aspect, whenever we were working with like finances, money, technically you could see the formula as 1 plus or minus the rate over the compounding time periods to the power of NT. A lot of times you'll see it written plus or minus, because if we're talking about decay, what's the word I'm thinking of? Depreciation, anything like something losing value, you're going to subtract the rate from 1 instead of adding the rate to 1. So that would give you a number, a base number less than 1, and then it would show the depreciated value. We're going to practice some of these things. And right here, it says to use the form A times B to the KT power, where K is a constant. I don't want you to get hung up on these formulas like, oh my gosh, what do I need to do for K? What do I need to do for A? What do I need to do for B? It's all the same thing. This formula is this. The only thing different is the base has been simplified. That's it. This B value right here is the simplification of 1 plus or minus whatever the rate is. That's it. And it's going to be something less than 1 or something greater than 1. All right. And then NT, that's your KT. And sometimes there is no K value. It's just because it's 1. All right. And so that's going to happen in different situations. All right. Do y'all have your calculators out? Grab your calculators because we're going to need them. All right. The very first part right here says to write a function f of t that describes the value after t years of a $2,000 investment that increases by 9% per year. Okay, right there you can identify this as exponential growth. Okay, because we're increasing by 9%. So to write my equation for f of t, I'm investing $2,000, so that's going to be my P. There you go, $2,000. Now, it increases by 9% per year. It doesn't say compounding monthly or anything like that, so automatically we're going to know that N is equal to 1, so it's per year. So we got 1 plus 0.09, because you have to change your percent to a decimal, to the power of t. That's it. So now if you were to write this out and kind of simplify that, if you were to write it in this form, what would be the value of B? 1.09. That's it. And is 1.09 greater than 1?
Yes.
That's growth. It doesn't have to be anything huge bigger than 1. It's just got to be bigger than 1, and that's going to show us growth. Okay, so this is definitely exponential growth. And I need to make sure y'all know this is growth because of that number right there. That base is greater than 1. Now, it says to describe the domain range and sketch a graph. So here's what I want you to think about. If you are investing $2,000, we are starting at $2,000, correct? All right. We don't need anything less than 2,000. We don't need any negatives. And we don't have time less than 0. At the very beginning, 0, we have $2,000. And that money is going to grow over time. There's a sketch of our graph. This is time, and this is money. All right. When you look at this, what would you state as your domain values? This is going back a little, previous units. What would you get? 0 to positive infinity. There you go. Bracket around 0 because that 0 is our starting time. What would you use for your range?
2,000.
There you go. Bracket around 2,000 and then infinity. Okay. All right. Now, let's take a look. Let's jump down here at part E. It says, for your function in part A above, find the value of your investment after 10 years. So can y'all do that for me? Can you see how much you have after 10 years? All right. Plug those numbers in and go. What'd y'all get?
4,734.72.
There you go. Students, anytime we're talking about money, always round to 2 decimal places.
It would be 3.
Okay, yeah, 73. All right, always round to 2 decimal places. But remember, the time in years, remember you plug it in for your exponent, and that's what our input value is. Okay, calculator does all that work for you. You just got to be able to set it up. However, okay, now let's take a look at part F right here. It says for this same function, solve to find how long it would take to double your original investment. Okay, try to solve this equation without using a graph or a table. So I don't want you to actually you plug this into your calculator to look at a table and find it. I want you to use your rules of exponents and logs that we've talked about to solve it. So here's what I'm contemplating. If we want our investment to double, how much did we invest?
2,000.
Okay. What's double that?
4,000.
So that would be our output. That would be our F of T, would be 4,000, right? So 4,000 is what we want to end up with. We started with 2,000. We are solving for time. Okay, now then, if you had to solve this, and pretend like I said no calculator. Leave your answer in exact form. Think about what would be your process for solving this. What would be the first thing you would do?
Divide 2,000.
There you go. Get rid of this coefficient. Divide both sides by 2,000, and you get 2 equals 1.09 to the power of t. Okay, now, I'm always going to go back to this. We are solving an exponential equation. Our variables in the exponent. What is the inverse of an exponential? A log. So if I want to undo this exponential piece right here, I have to eliminate my base, so I have to log both sides. What do I use to log both sides with?
Either natural log or log base 10.
Okay. Here's where, let me ask you this. What log base would I use in order to eliminate this base and get t out of the exponent to solve for t?
1.09.
Huh?
1.09.
I would have to use a log base 1.09. And that sounds real foreign. But if my goal is to write this in an exact form so that t's all by itself, that is the easiest way to do it. Okay? Now, We can use natural log and do that. It's going to take a lot more work. Since we have fancy calculators that will change the base for us, that's what I want to use on these, okay? So we're going to use a log base 1.09 of 1.09. Oops, wait a minute, what am I doing? 1.09 on both sides. So that we can get t out of the exponent. Now, that looks really funky, right? Log base 1.09 to what power is 2? All right, we're going to get something a little bit different than what we're used to. All right, what you're going to do is just plug that in the calculator. Straight up plug that in the calculator. About how many years would it take?
8.2.
Okay, it's about 8 years. I want you to physically type this in to make sure you remember how. The more times you do it, the more you'll remember the how to find it. Do y'all remember to hit the math key?
Yeah.
Hit math. Arrow up a couple of times to where it says log base, and then you can type in 1.09 as the base number, and then 2. Now, in college algebra, they may have done this a little differently, but as far as simplifying, if I want to solve for t, this is, for time, this is the easiest way to do it. Yeah. Did they do it differently in there?
I don't know if we've gone over this. I don't pay attention.
That is, okay. Because I know they've been doing this a lot this week. I'll ask Miss Colling and find out for sure how she would approach this problem. All right. Now then, let's go back up to part B. This one wants us to describe, write a function that describes the value after t years of a car, $25,000 car that depreciates. If you haven't ever gone to buy a car or anything like that and dealt with any type of business stuff, depreciation means something loses value over time. And it depreciates at a rate of 15% per year. So, since we are depreciating, right here, instead of a plus, we're going to have a minus, okay? So what we've got is V of t equals, and we've got a $25,000 car at 1 minus 0.15 to the t power. And right there, we would identify this because our base would be 0.85, so this would be decay, exponential decay. And I want you to think about what this would look like if you graphed it. So we bought a car at $25,000. Are we going to go above $25,000? No. So let's just mark it off right here. This is $25,000. This is money, and this is time. Okay, and it depreciates, so the value's going to go down. And anytime y'all buy a car, it depreciates a lot faster at the beginning than it does at the end, as soon as you drive it off the lot. Okay. Looking at this graph, think about what is our domain? What is our time frame? 0 to infinity. Now be careful how you state this. What would be your range?
Well, it would be negative infinity to 25.
It'd be 0 to 25K.
Because this is your range right here, right? Okay, so we are approaching 0. Do we ever reach 0? No, it'll be worth pennies, or nobody will want it, it'd be junk, but technically it's not 0. So we're going to do a parenthesis 0 because you always state your domain and range from least to greatest. You always do that. And its maximum amount is 25,000. And we have to bracket that because we do equal 25,000. All right, so just to kind of get you an idea of what that looks like. Let's see. Let's take a look now at part C. Write a function that describes the population after T days of a colony of 1,000 fire ants that doubles in population every 13 days. Okay. This one is pretty snarky. And this is going to look a little different than what you're used to. So I want to kind of talk you through it. Is it a growth or is it a decay?
Growth.
Definitely a growth. Okay. So we've got P of T, the population over time. And what are we starting with? 1,000 ants. Okay. Now, if it's going to double, here's a way that I want you to write your base number. If we look at it in this form, 1 plus the rate, okay, so it's growing 100%, right? It's growing 100%. And 100% as a decimal is what?
1.
And what is 1 plus 1? 2. So technically our base number is 2. That's because we're doubling times 2. But we only take it times 2 every 13 days. So here's what we have to consider. Time is going to be in terms of days. But on day 1, have we doubled? No. When T is 13, we will double. So how can I write my exponent so that when time is 13, my power is 1? Exactly. T divided by 13. When you reach that 13th day, you will have a complete double. What happens when you reach the 26th day?
You'll double it again.
You'll double it again. And then the 39th day, you'll double it again. So this is done just a little bit differently. So in our exponent, we're showing how often we're going to double. So we're still growing in between. We're still growing in between the doubling effect. But we have to account for that. It has to be on that 13th day that we actually double. Okay. Now, let's take a look. Let's think about what this would look like as a graph. We start with 1,000 ants. Time, and we're going to put population right here. All right, and we're definitely growing. This is a growth situation. What is our domain? 0 to infinity. And what is our range? 1,000 to infinity. There you go. Okay. Now, I'm going to skip down to part G. I want y'all to look at part G, because it says using this function rule right here, solve to find how long it would take. So we're solving for time for the ant population to reach 10,000. Okay. So we want P of T to be 10,000. All right. Think about how we would go about solving this for time.
Divide by 1,000.
Divide by 1,000. So we get 10 equals 2 to the power of T over 13. Now, we're solving for T, right? How do we get T out of that exponent?
Multiply 13.
Huh?
Multiply
Okay, we got to get rid of the base. We got to get rid of the base first. Log base 2. If we log base 2 on both sides, we get t over 13. Okay. Now, what would be the next step? Multiply by 13. So you're going to type into your calculator 13 times log base 2 of 10.
43.18.
Yeah. Okay, so if we do it by the nearest day, it'd be about 43 days. Okay. Now, and folks, this is why I like eliminating the base whenever I'm trying to solve for that variable by using one of the same bases. You can natural log those and bring the exponent to the front. You can do all of that we've done before. This is sometimes, if you're using a word problem, though, and you want a definitive answer number, this is the easier way to do it. Okay, much, 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 much easier. All right, next one, D. Write a function that describes the remaining mass after T years of a 100-gram sample of radioactive compound with a half-life of 31 years. That goes back to our half-life formula that we discussed last week. Okay, does anybody remember what it is? What did we start with? 100 grams. And what is the base number that we use in half-life? The E? The E, okay. So 100 E, and remember that's to the negative T natural log of 2 and over H, and since H is 31, we would put 31 under there. So this would be our function rule for half-life. All right, let's show what that would look like on a graph. So we've got time and we've got mass. This is grams. We're starting out at 100. And is this growth or decay? Decay, so we're decreasing. So this is definitely decay. And then what is our domain? Our time frame? 0 to infinity. What is our range? 0 to 100. And do I put a bracket or a parenthesis for 0? Parenthesis, good. 0 to 100, and 100 gets the hard bracket. Okay? Keep in mind, folks, this isn't, we started at 100, and then we're approaching 0. But you always write your domain and range in order from least to greatest. You always do that. Okay? Never do it backwards. It's just wrong. You don't wear your pants backwards. Don't write your numbers backwards. Okay? All right. The last thing we're going to do. This half-life formula is exactly the same thing as this formula right here. Okay? It's just written a little bit differently, but it is actually can be expressed exactly the same. So I want to show you how you would turn the half-life formula into this basic form right here. So we've got, I'm going to go ahead and write the formula down, and then we're going to tweak it a bit. Okay, what I want to do is this whole, Since I've got the natural log of 2 up in my exponent, remember, if you have a base, your base number is the same as your exponent log, you're going to be able to cancel those out. So I'm just going to rearrange the order of my exponent into natural log of 2 to the negative t over h. Because when I take a power to a power, remember you just multiply those, so I'm not changing the value, I'm just writing it to look different, but the value is the same. Now, e to the natural log of 2, what does that simplify down to? Just 2. Just 2. And then 2 would be to the power of negative t over h. Now, what can I do to that 2? Or how can I rewrite 2 so that I get rid of the negative exponent? What can I do to the base number? 1 over 2. Remember, do the reciprocal. If we want to eliminate the negative exponent, do the reciprocal of the base. So it's 1/2 t divided by h. Okay. Now, t divided by h, if we want to write that in the form of kt, k is actually just 1 over h, and time is t. So this is n sub 0 times 1/2 of 1 over h times t. That is the same thing, the exact same thing as a times b to the kt power. A is n sub 0, b is 1/2, k is 1 over h, and t is time. So even though these formulas look super different, they can all be expressed. They all kind of work their way around and have the same meaning. It's all the same thing. Okay? If you look on page 23, that's some more practice problems over what we've just been doing. Tomorrow I have assigned a delta math, but I'll probably do the delta math on Thursday if we test on Friday. So what I need y'all to do is make sure tonight you get pages 20 and 21 finished. And then tomorrow we can work on page 23 in class. How's that sound? Okay? All right. So y'all have an assignment to work on tonight.
Can you do release of those math?